You take it.
Yeah.
All right, let's go. Zach, wait for us here. Let's
Restart.
simmer down.
Actually, no. It sounds like you all are having more fun. Let's just talk about that instead. You all pretty much have the answers here, right? You just go home. Call it a day.
You stuck with us this long, Zach. Come on. Last class. Don't give up on us now.
Okay.
Last class.
All right. Okay, so Fannie Mae and Freddie Mae.
Where are you?
Number 3 on quiz 5.
Oh, okay.
Fannie Mae says that there are differences in knowledge between college-educated and high school-educated homebuyers. So they conduct a sample and find that 62% of college homebuyers know something about a mortgage. Only 60% of high school homebuyers know something about a mortgage. And we've got a sample of 500 college kids and 259 high school kids. With regard to this particular issue, can you use the sample results to reject the no difference in population proportions null hypothesis for the two populations represented? All right, what does that mean, reject the no difference in population proportions? I'll give you a hint. It's going to tell us something about our null hypothesis.
It doesn't matter what your education is,
Yeah.
whether or not you understand the mortgage.
Exactly. That is a brilliant way to say it. How would we represent that with proportions and equal signs?
Um,
All right, I'll give you a hint. It's proportion, college. I'll start you off. It doesn't have to be V. Gale. She answered the first part of the question. It could be someone else. Null hypothesis is proportion of college kids. This is the whole population. Is it going to be greater than, less than, or equal to?
Greater than. No.
Sorry, Carlos. Sorry, was that too? All right, so a no difference hypothesis.
No.
Equals, yes. I'm sorry. I shamed Carlos into looking down, but he's got it.
I was rereading.
I'm sorry about that. All right, no difference. You could never fail me, Carlos. Never, ever. Never, ever. You're the one who invented p-value.
I was here.
Carlos invented p-value. Let's never forget that. All right. Proportion of college kids is the same as proportion of high school kids in the whole population. Alternative hypothesis, proportions not equal. All right. Ready? So, one-tailed or two-tailed test?
Two-tailed.
Yes. Two-tailed test. There are two ways of disproving this hypothesis. So, we've got a difference in our college sample of 62 and our high school sample of 60. So, remember, we can always use a z-stat in proportions. Everything's cool there. So, our z-statistic in evaluating this null hypothesis is going to be 0.62 minus 0.60 divided by our sampling distribution, our standard deviation of the sampling distribution of the sample proportion. All right, and to do this, to get this sampling distribution, standard deviation of the sampling distribution, actually I forgot to put standard deviation on the answer. So the third line of the answer, it should say standard deviation of. Standard dev of. Standard deviation of the sampling distribution of the sample proportion. Difference. Got it. Yeah. So 2 mistakes on that. Sorry about that.
It better be.
Yes. So there's a little nuance we need to take care of to get that figure. First thing we need is the pooled sample proportion. So we do a weighted average, 500 people in the 62%, 259 people in the 60%. What is the weighted average of that? Well, that's what the first two lines are calculating. Yeah, and it's 61.32%.
That's the P-bar pool.
Yes.
Pool.
P-barred pool. Yes, P-barred is the sample proportion pooled. All right, and then when you got those two notations, that third line should start standard deviation of sampling distribution of the sample proportion and should end difference. So interject a difference. So standard deviation of the sampling distribution of the sample proportion difference. That's how that line should have read. And that's going to be our pooled proportion times 1 minus the pooled proportion divided by sample size 1 plus pooled proportion times 1 minus pooled proportion divided by sample size 2. Square root that whole thing, and we get, 3.73%. So 0.0373. Okay, and that test statistic is going to come out to 0.54.
Test that or Z-stat?
Z-stat.
I said test statistic. I could have also said Z statistic.
Okay.
Test is general. I'm willing to admit when I'm wrong, but I didn't say T statistic. That would have been definitely wrong.
Yeah. Statisticians would not allow that.
Well, actually, statisticians would say you're being a little bit more conservative. Fine. But you don't have to be that conservative. Okay.
Done.
Good point, Jonathan. So what do we do from there? 0.54. What is that? Just give me an eyeball on that. What do we think about how that's going to determine reject, not reject? So assuming the null hypothesis is true, is this a crazy result? No. No, it's only a half standard deviation above the mean, assuming that what the bank says is true. To be a little more exact, let's find the p-value. So what's the p-value for an answer at least as extreme as 0.54? P-value, okay.
So when we find it, are we doubling it?
Good question. So when we find it, if it's a two-tailed test, we need to double it.
Right. So when we go to Z-table, we're looking for 0.54, and then we're doubling it.
Yes.
So
Yes.
0.291.
But, yeah, is that what you... Okay, but then there's another nuance in making sure you're reading the table correctly. When you look at 0.54, is it going to say... What's it going to say? Well, we know it's two-tailed, and we know we double it. That's great. But when we look on the table for 0.54, what's it going to say? Like, look on the chart.
It's going to
I would everyone do this if I were you. I would just... Okay, go ahead. Really? On negative? Positive. Why are you looking negative? I said point.
It's a positive point.
Oh, it's a positive.
Yeah, it's positive.
0.705.
Okay, all right. So I made it more confusing in a way. You were jumping right to the right answer, but if you were to look at 0.54, you would get 0.7. All right. What do you do? What's the next step there? Then 1 minus that. 1 minus that gives you what?
Total surface area.
So when you look on the chart, you get what, Josemel?
0.7054.
7054. All right, and then you do 1 minus 0.7054, and that equals what?
0.2946.
2946. Are you done?
No.
Then what do you do?
2.
Double it.
Times 2 equals
5892.
0.5892. Okay, and then you're done.
That's all for people.
So then the p-value here is wrong.
Yeah.
Because I said 0.5917.
Yes.
All right.
Yeah, let him know. Tell him again.
No.
Nah, tell him again.
That's cool. That's cool.
Go ahead.
If you
Oh.
round that up, it's.
If we round it up, it gets to be 0.5917. Oh,
Gotta love
gosh.
math humor. Gotta love math humor.
Yeah. All right. I will take a closer look at that. But what for this particular quiz, I had different versions, a different quiz version. So I just cranked them all out on Excel. So there may be a difference between the Excel value I got and the answer in the table. All right. All right. So we're ready to move on? All right. Let's do it. Great work. Let's move on to regression analysis. All right, let's skip the true false stuff. You can read that in your leisure time. Let's go to question 6. All right, coefficient of determination. What's the coefficient of determination? Also known as R squared. Fantastic. And R squared tells us what? I'll start you off. The percent.
0 to 1.
0 to 1, yes, and it tells us the percent of the variation that can be explained by the regression equation.
Period.
You got it. Here, you got it. All right. So R squared, the same thing as coefficient of determination, percent of the variation that is explained by the regression equation. So the two components we need to answer that. The SSE is 20. That's an error sort of left over when we draw the line of best fit. The SSR is the amount of variation that is explained if we were just to compare it to an average. And SST is total variation if we were to compare everything to just a straight average. So the two things we need for this are the SST, the total variation compared to average, and the amount of that variation that is explained with the regression line of best fit. And so to get that percentage, we take the SSR divided by SST. 800 over 1,000 is 80%. You like that? All right, another useful metric. And if you recall, there's two parts to this regression stuff. First, we take the sample data and we do a line of best fit. And we say, how well does this line of best fit the sample data? And we have coefficient of determination, we have correlation coefficient, and we're also going to recall standard error of the estimate. Those three things, they tell us how well the regression line fits the sample data. And then the next step is, what if we were to infer things about the whole population? What if we were to try to take that sample regression line and make an estimate predicting the whole population? What sort of extra confidence interval would we need to add with that? So right now we're just looking at how well does this regression line fit the sample data. And we have one metric, R squared. Well, it explains 80% of the variation. Second thing we have is the correlation coefficient, which is similar to R squared. It is the square root of R squared. A number, an R that is close to 1, means it explains it on a 1-to-1 ratio. So 1 explains it exactly. It would be correlated on a 1-to-1. Like 1 unit change in, say, time spent online would have an exactly 1 unit change in money spent
So
online.
they're directly related.
Directly related.
Okay, so.
A -1 would be a directly inverse related. And something close to 0 would mean a small relationship. This correlation coefficient gives us the benefit of being positive or negative. So positive relationship, negative relationship, inverse relationship. Okay, and that's the calculation. If you take the square root of R squared, you get 0.89. All right. let's move on. Ready to move on to the next one? All right, standard error of the estimate. So this is a standard deviation-like figure. How well does this line best fit the sample data? On average, how far is each point from the sample data? Well, we take the error of all the sample data squared, added together, is the SSE, and that's 200. We divide that roughly by the sample size, but not quite the sample size. Sample size minus 2, which gives us 4. Take the square root of that because the SSE was all squares, sum together, and the standard error of the estimate is 7.07.
So that 0.5 is square root.
Yes. Yes, exactly. All right, so now, once we've looked at how well this regression line fits the sample data, we want to think about how we can infer various things about the whole population, how we can predict relationship on the whole population. So now we want to calculate a 90% confidence interval for the population slope of the following sample. So what's the population slope in our regression equation? Or excuse me, what's the sample slope in our regression equation?
8.5.
Yes. All right, so that's just based on a sample. So to infer that on the whole population, what do we need? Well, we need a confidence interval. All right, so we just want to say, it's between an interval. 8.5 is going to be our point estimate, so it's 8.5 plus or minus some amount. So, and it's going to be some either z or t value times a standard error metric. So let's first talk about the z or t value. For regression, we use t value. We don't use z. So we'll just leave that at that. And how do we calculate degrees of freedom for any regression? N minus 2. And as Jonathan pointed out when we got to multiple regression, that's actually n minus k minus 1. Well, it's n minus 2 because there's only 1, because k is 1. Yeah. So n minus k minus 1 is going to be the degrees of freedom we use. We look on the t distribution for 90% confidence interval, and we get a t value of 2.132. All right, and what's that 2.26 number?
Standard deviation. Standard distribution of the sample.
Yep, so that's already given to us. That's not even a standard deviation. We don't have to divide by the square root of n. It's just already spelled out for us in this problem. Standard deviation of the sampling distribution of the sample slope. Yep, it's 2.26. So all we need to do is take 2.13 plus or minus of those, and we've got our confidence interval. On number 9. All right, we good there?
Yes, sir.
Like it? Fantastic. Ready for number 10? All right. So let's do a hypothesis test to determine if the population slope is statistically significant. Let's use a 1% significance level. So when we say statistically significant, we mean that it is significantly different than 0. Because if the slope were 0, that would mean an extra 3 hours spent online has no relationship to more money spent online. Multiply that 3 times 0. If it is something besides 0, then it is a statistically significant relationship. So let's erase all of this. Let's see. The null hypothesis is that population slope is the population slope, this big B, equals 0. Means there's no relationship between the independent and dependent variable. Alternative hypothesis, population slope does not equal 0. Two-tailed test, 2 ways to disprove this. So let's look at how we're going to calculate our t-stat, because we always use t for regression. All right, so what's the difference between our 8.5 sample slope and 0? All right, how big is that difference? Well, it's 8.5. More specifically, we want to know how many standard deviations above 0 it is. And if it's like a half a standard deviation above 0, and we had one of those earlier tonight, we're like, yeah, it's no big deal. That's not anything worth writing home about. That's nothing that really proves something overwhelmingly. If it's like 5 standard deviations above 0, then now we're talking. So what is our standard deviation figure in this hypothesis test? It's actually just given for us because we really don't.
9.54.
Close. Yes, 2.26.
Oh, because it's the slope.
Yep. No
A
problem.
little b, right?
Yes. Well, the Andrew, the little b is 8.5. This standard deviation, or maybe you said this. I'm sorry, I misheard. So standard deviation of little b, is that it?
Yeah.
It's
Yeah.
given.
Is that what you said?
Yeah.
Yeah. Okay. Sorry about that.
But that's of the population slope, right?
This is the sample. Little b is the sample slope.
Okay.
Big B is the population slope. So this is 2.26. Okay. So how many standard deviations is 8.5 above 0? Well, it is 3.76. All right. So we've got our test statistic. Let's do critical values. This is a one-tailed or two-tailed test? Two-tailed test, right? So we're looking for both a positive and negative rejection region. What is our significance level? Yep, 1%. All right, so we're looking for 1/2 of 1% here, and we're looking for 1/2% here. All right, we always use t for regression, t distribution. What is our degrees of freedom? What's that? 2? I don't think so. Our n is 4, so n minus. What's the magic formula, Jonathan?
N minus k minus 1.
Yes. All right. So 6 minus. What's k in this case?
How many?
K is number of independent variables.
About 2
2 or 1? Which one?
or 1?
1. Yes. 1 minus 1 minus 1. So 4 degrees of freedom. So we need a critical value for 4 degrees of freedom and 0.5% in each tail. All right, so you have 2 options. You could look in the back of the book, or you could look on the answers. I would accept either.
I'm sorry.
Critical values.
Oh, it's 4.604.
Yes, 4.604, negative 4.604. Okay, so what is the decision then? We got a t-stat of 3.76, and we have critical values, negative 4.6, positive 4.6. Absolutely. Absolutely. Good job, Andrew. So, balls within. It's worth noting, though, this seems like a pretty significant T-stat. 3.6. Why is our standard so high? Why is our standard for rejection so high?
Because we use the T distribution, which allows for a little bit more wiggle room.
Yes. Yeah. So T distribution, not only a T distribution, but basically two other T distribution. Yeah, two other things I'm looking for as well.
0.01.
Yeah,
Oh,
a very small significance level. That's one reason, and the other why our standard is so high.
Oh, we have two independent,
The degrees of freedom sign.
Degrees of freedom is really low.
really low.
Very small sample size, only 6.
Because we have two variables. Is that what you said? Two
No,
independent,
because
not
we have
variables.
one.
We only have one independent variable,
Okay.
but the key here is we only have a sample of 6. So it's a very small sample.
Gotcha.
So it would not be unusual for us to get a large extreme value with only a sample size of only 6. If we had a sample size of 30, then we would not have such a high standard for critical value.
Good question.
Yes.
I might be missing something. You have, the sampling slope is the 2.26, but the 8.5, isn't that the population slope? So shouldn't that be a capital B?
This is our sample slope, 8.5.
No, go there. See there? It looks like either a 6 equals 8.5, or it looks like a small b equals 8.5.
Yep, small b. Small b.
It is small b.
Yep. Small b.
Okay.
And we want to know what is big B. Is it significantly different from 0? Okay.
Kind of.
Yeah. Well, I mean, it's 8.5 difference from 0.
Yeah.
Question is, how many standard deviations different from 0 is it?
So,
3 point.
okay, so 3.76. So
Yes.
because the 3.76 is within,
Yeah.
then we're not rejecting.
Yeah. It's 3.76 standard deviations, but it needs to be 4.6 standard deviations
To be
difference
rejected.
because we have such a high threshold. And we have a high threshold because we want a 1% significance level, and because we have such a small sample size.
Isn't it easier to just compare it and if it's less than,
Compare the
critical value,
compare the 3.76.
4.6.
Yeah. We say it's within this range. Wait, what did I do? Did I do something different than that?
No, it just, too much wording confuses me. I just
Okay.
do less than or equal and then I know whether it's fail or reject.
All right. All right. We ready for quiz 7?
Yes, sir.
Let's do it. This is the Zach Williams not teaching stats class.
Oh man, exactly. It's not teaching stats.
See if I can redeem myself now.
Oh yeah, this was that class. You're right. That Williams hard, right? What? Oh, straight up. I guessed I was doing that.
All right. So for the first problem, we've got a multiple regression equation, which is asking us to predict home price with technically 3 independent variables. One of them is an independent variable that we're used to, which is square feet, right, in hundreds. So if you have a 1,200 square foot house, then you have 1,200 square feet. And for each 100 square feet, you're going to multiply by $15,056. So your house is 1,200 square feet. Miguel's house is 1,300 square feet. All things being equal, I'm going to say her house is going to sell for $15,056 more. Alright, we're going to have an intercept of 234,767. So you add that to your square footage. And then there's these dummy variables, x1 and x2. What do those mean? How do we interpret those?
You interpret dummy variable as zero. It's 1 or 0.
Yep, 1 or 0. In which instance would it be 1? In which instance would it be 0?
I'm going to give you some indication.
If it's within the same zip code, it'll be a 1. If it's not, it'll be a 0.
Fantastic. So it's just a yes or no. You check the zip code, check the table, 1 or 0.
I remember this question.
And then, so let's look at the zip code, and let's try to think which one of those is the rich neighborhood, which one of those is the middle class neighborhood, which one might be the poor neighborhood.
This was easy.
Yeah, no, you can figure it out.
Oh,
Look at the regression equation, and then look at the zip codes.
yeah. Okay. So the 98029
Is what?
is x2.
Yeah, but is that the rich neighborhood, the middle class, or the poor neighborhood?
Middle.
Which one? Just tell me which one is rich. Just make a statement.
I think the 98026, the first one, with the double dummy variables, is the rich neighborhood.
I like it. Why do you think that?
So it has a positive x1.
Because you don't have to subtract off anything in evaluating the estimated value of that house.
I'll take that. That's not what I saw.
So you put in 0 for the x2, 0 for the x3, and that makes your predicted home price higher
Yes.
because x2 and x3 are negative. So if you live in 98026, you have no negatives.
For, I guess the middle class would be x3.
Now, tell me which zip code would be middle
So middle
class.
class would be 98029 because it has a lower negative in x3.
You think that would be middle class? I disagree with that.
So we have to.
Oh.
Oh.
The other one. Yeah,
What would be the other one?
9116?
98116 would be middle class.
Why?
98116.
The reason why I said use that one, 98029, is because x2 has a higher negative.
Yeah.
So I didn't want to zero that negative to make it middle class.
Yeah, so so if you have to put in a 1 for x2, that means your house is $106,748 less in value than someone who doesn't have to put in a 1 for that variable.
So I did that.
So,
So you want to zero it to be the middle class. The bigger.
I don't know, want, not want. It's just we're just predicting home values.
I'd be totally fine if you left this off This is
All right, well, let's back up a minute.
Yeah.
So we're predicting home price.
Yes.
All right, there's a intercept component, $234,767. Any home, just for even if you don't have any square feet, technically, your house would be worth $234,700. That many dollars.
Gotcha.
But the intercept, we use it mathematically, but it doesn't have meaning the same way the slope has meaning.
Okay.
It's just the math, so we won't get too caught up on interpreting the intuition there. What we do get caught up interpreting the intuition are the sloped coefficients, x1, x2, x3. So x1, we know that we have, for every additional 100 square feet, our home is expected to increase in value by 15,000. So more square feet, more value. And then, if we have to put in a 1 for x2, which means, if you look at the table, under which situations would we have to put in a 1 for x2?
98029.
Yeah, if we live in 98029, we then put in a 1 for x2.
Give me a second.
And all other things being equal, that house is worth $106,000 less.
Yes.
All right. If we don't live in that zip code, we put in a 0, and we just ignore that part. If we have to put in a 1 for x3, tell me on what zip code might we live in where we'd have to put in a 1 for x3.
98116.
Yeah, if we live in that zip code, we put in a 1 for x3.
And your house would be 26,726,000 less.
Yes, all other things being equal. All right. So,
So your rich neighborhood would be X3.
no. There's only 3 neighborhoods, and they have 3 zip codes. The x1, x2, x3. Those aren't neighborhoods. Those are independent variables. So, tell me the rich neighborhood.
98106.
98116.
Oh,
No,
98026. Because you're not losing any value per square feet.
Yeah, the correct answer, the rich neighborhood is 98026. Let's make sure everyone. Does that make sense, Victor?
Yeah, because you're not subtracting anything else.
Yeah.
All right. Now tell me the most poor neighborhood.
Let's see, X2.
Yes, because if you live in that neighborhood, you have to subtract off a big chunk. So you live in that neighborhood. Ellie lives in the rich neighborhood. You have your house, all things being equal, $106,000 less. And in the middle neighborhood, where all things being equal, your house is $26,000 less, is the 98116. Okay, so if I give you the information about how many square feet you have and which neighborhood you have, you tell me what?
The predicted price.
Yep. I'm not going to say anything more than that, but I can repeat that again if necessary. Or even if not necessary, I'll repeat it again. So you tell me your square footage in your house. You tell me what zip code you live in. I tell you the predicted value of your home. And you crank that out and tell me on the exam. We good? All right.
How did we get 429 and 139? I'm sorry.
Sure.
Where did that 20 come from?
All right. So can someone explain where that 20 came from?
It's part of
2,000 square feet.
Yep.
Got it.
it's part of this, right? There's the line. X1 is defined at 100 square feet for examples of 1,200 feet. X1 would be 12. They give us 2,000, so you just take away 2 zeros.
So now X1 is just telling me that if it is a certain square footage, I'm adding that?
Yep.
Okay.
Whatever square footage. Suppose your house was 3,500 square feet
It'll be 35
times 15,000. Yep. Yep. And then you figure out which zip code you live in and do that calculation.
So, I have a question.
Yes. No.
This says correct feedback, incorrect feedback.
Oh yeah, that's just the way Blackboard works. It's
Oh, because
yeah,
it looks exactly the same to me.
Yes,
So I'm
it's-
looking for like,
it's the same. Yeah,
okay.
it's the same. It's
I'm like, wait.
sorry about that. It's so if you give
It's a sanity test.
Say- it's a multiple choice question. So if you got it wrong, you would get the incorrect feedback. If you got it right, you would get the correct feedback.
I'm like,
Okay. All right.
missing a whole piece.
Number 2.
Alright.
All right. Below is an output for regression analysis attempting to link dependent variable y to independent variables x1 and x2 using a sample of 18 observations. Build a 95% confidence interval estimate of the regression coefficients, big B1 and big B2. So big B1 is the whole population slope for 1. Big B2 is the whole population slope for coefficient 2. All right, and the x1, x2. I guess we could put those are little b's. We could call those little b's the x1, x2.
So sample.
Yeah, sample slope. Yeah, that would be fair if you wanted to call those little b1, little b2. All right, so little b1 is negative 1.4, little b2 is 1.1, and we have standard error figures. And let's call those standard error figures standard deviation of the sampling distribution of the sample slope. So let's do 95% confidence intervals. Do we use for regression, do we use a Z or a T? We use T. How do we calculate degrees of freedom? Tell us, Jonathan.
It's a n minus k minus 1.
Yeah, it's always n minus k minus 1. All right, and what is k in this example?
This is two. There's two variables.
Yeah, k is independent variables, and there are two independent variables. So degrees of freedom is 18 minus 2 minus 1. Carlos has helped us out with this before.
Huh?
Oh, sorry. Sorry, it's being funny.
15.
15, yes. Yes.
I was
All right.
listening.
15 degrees of freedom, 95% confidence, and it's going to be a two-tailed situation because we could make a mistake, positive or negative on the slope. If we were to look in the back of the book, 15 degrees of freedom, T-tail test, 2.5 in each tail, we would get 2.131. So, all right, so for the first one, little b1, negative 1.4, we're going to go plus or minus our 2.131 times the standard error. And we're going to get that confidence interval. For little b2 is 1.1 plus or minus the appropriate t value times the standard error of 0.58. And notice that that's giving us a confidence interval for big B1 and big B2. So we've got the sample slope, little b's, or x's, whichever way you want to look at it, and it's inferring that the whole population slope would be the big B1, big B2. We liked it. Alright, we're good there? Alright, I'm with you. I'm with you.
No, with you.
I won't give up on you. I won't give up on me. The output below is from a study of multiple linear regression to link independent variable y to x1 and x2. The sample consisted of 28 observations. Alright, so we've got an intercept. We've got little b1 or x1, little b2 or x2. We've got standard errors. Alright, if we needed confidence intervals or we wanted to do a hypothesis test, we could do standard errors. But we've actually, in this, we've even got t-stats. And those t-stats, the reason why I felt comfortable giving you this table is there are some homework questions which direct you to understanding that the t-stat is just a no difference hypothesis test. So if you're a difference between zero hypothesis test. So is the slope 1, negative 1.2, is that significantly different than 0? Well, the t-stat you would calculate is negative 1.364. How about the 3.5? Is that significantly different from 0? You'd calculate a t-stat of 3.125. Okay, so you could look at the t table and find out if that passes muster on the t critical values. You could do that. In fact, you need to for this problem. And you're also given a p-value for that t-stat of slope 1, a p-value of 18.5%. All right, so let's just go straight to the correct answers. The correct answer is the last one. And let's just read that through and make sure we're comfortable with why that is accurate. Yeah, so for B1, also known as X1, the p-value is 18.5%. Since 18.5% is higher than our 5% significance level, we can't reject the big B1 equals 0 null hypothesis. Is everyone comfortable with that statement?
Since it became greater than
Yeah.
because it is reject, yeah.
Yep.
Okay.
Yeah, so that's saying if we were to do a null hypothesis, saying x1 equals 0, we would not get overwhelming evidence to the contrary. We would get something that happens, say, 18% of the time. We don't consider that overwhelming, so we can't reject the null hypothesis. This coefficient is not statistically significant. For little b2, the t-stat is 3.125. From the table, the critical value for a 2.5% tail and 25 degrees of freedom is 2.060. So let's back up a minute. Let's actually find that t-value, or think about how we would find the t-value. So we've got 28 observations, which is how many degrees of freedom, Jonathan?
25.
25. And we're at a significance level of 5%, 2.5% in each tail. So we flip back to the t distribution, 25 degrees of freedom, 2.5% in each tail, and that gives us a t critical value of, outstanding, 2.060. So if we were to look on the table, we would see that is correct. And we would know that 25, we would know that that t-stat of 3.125 is greater than the t-critical value that we found in the book. So we can reject the slope 2 equals 0 null hypothesis. This statistic is, this coefficient is statistically significant.
You're saying that it's significant?
Yeah, because it is it's 3.25 standard deviations above 0.
So that means that the null hypothesis is equal to 0.
Yes,
So there's no correlation.
right. It's not a correlation issue. It's
Or
just
significance issue.
yes. It's just, is it significantly different from 0?
Okay.
Well, it's 3.125 standard deviations above 0. And we decided based on our parameters that if it's 2.06 or greater standard deviations above 0 or below 0, then we're going to call it significant. All right. So, number 4. Are we good? Yeah, we're tired, but we're good. Or at least not dead. Okay. So for this one, we need to know mean square regression, mean square error, and how we combine those two for f-stat. So mean square regression is going to be our sum of squares regression, which is 2330. All right, that's the sum of squares, and it's in the regression part. So it's 2230, and we divide 2230 by 2, and 2 is what?
Degrees of freedom.
Well,
Oh,
yeah,
there are two variables.
yeah, it is degrees of freedom, sort of, but it's 2 variables, 2 independent variables. I would not get confused by that degrees of freedom column. So we divide that by 2, the number of independent variables, how much of the regression each variable, or how much of the SSR each variable explains. Then how do we get this mean square error? Just MSE. Well, we take the sum of squares error, which is 6620, and we divide that roughly by the samples, number of samples.
25.
Yeah, so 25 is roughly this number of samples, but number of samples minus,
Degrees of freedom. Minus K minus 1.
yep, minus k minus 1. In this case, k is 2, 1 is 1, 28 minus 3 is 25. So, all right, so we take 6620 divided by 25, and we get 264. So then, for the f-stat, remember the name of the game with the f-stat was the explained variation divided by the unexplained variation. All right, if that's close to 1, then this whole regression equation that you just calculated doesn't really explain much. But if it's significantly different than 1, then wow, we've got something. We've got explained variation, 1225 in the top, unexplained variation, 264.8 in the bottom. All right, those pretty different. Those, in fact, 4.211. So we like that number seems different than 1. Our next step, if we were doing a hypothesis test, would be, or actually, you know what? I guess you all don't need to worry about that because I already told you that the exam questions will actually, wait a minute. I think you might have to actually calculate, yeah, the next one you have to calculate an F test. Sorry. Okay, so the 4.211, so we could, if we needed to look on the F table in the back of the book, we would have numerator degrees of freedom of 2. We would have denominator degrees of freedom of 25. And we would have whatever our significance level was. And we could do a reject, not reject scenario there. Okay. Are we good there? All right. Let's do number 5. All right. So here we've got 2 independent variables. Alright, we've got a sum of squares regression of 1828. We've got a sum of squares error of 3282. We've got a sum of squares total of 5110. Alright, now pop quiz, how do we get from 1828 to 914?
SS divided by D.
Yes. How do we get from 3282 to 218.8? Yes, divided by 15. All right. How do we get that F value of 4.177? Yes. We divide explained variation divided by unexplained variation, we get 4.177. And the p-value for F is what? Yeah, 3.6%. Yeah, if we were doing a hypothesis test and said we're at a 5% significance level, what would we conclude? Which is, we're not really used to going this fast on setting up hypothesis tests. But what this p-value is, it's saying a null hypothesis that this whole regression equation, all taken together, all the variables, tells us nothing worthwhile.
There's nothing significant.
Yeah, that's the null hypothesis. Nothing significant in this regression equation. The alternative hypothesis is at least one of the coefficients is significant. Okay, and then we have a test statistic that has a p-value of 3%. Now what do you think, Jonathan?
We can reject.
Yes.
Because it's they are 0. They don't have
Okay.
burned out.
Alright.
Burned out.
The p-value is less than the significance?
Yes.
Reject. Okay, so let's go straight to the right answer. It's A and C. Let's quickly read through these and make sure we know why those are right. All right, we can use the p-value for the F to make the call. Since the p-value is 3.6%, is less than 5%, we can reject the all population slopes are 0 null hypothesis at this significance level. Yes, because 3% is less than 5%, we can reject the all B's are 0. All right, that is, A works. Now how about C? We can use the F value to make the call. Since the F value, 4.117, is greater than 3.682, we can reject the all B's are zero null hypothesis. Alright, tell me how we got that 3.682. It had to do with looking in the back of the book at the F distribution. Yeah, the F chart. And what were our degrees of freedom? So this is the funny one with numerator degrees of freedom and denominator degrees of freedom. So we have the numerator degrees of freedom is number of independent variables, just 2. Denominator degrees of freedom is
N minus
n minus k minus 1. Yep. And if we were at the 5% significance level, we would see 3.682 as the critical value.
Sorry.
Nothing personal. Nothing personal.
No, it's not personal.
Alright. Unless you maybe mean it to be personal. I remember, let me tell you a brief story as we flip to Class A. I remember I sat through one day of a government class in college. And I thought the teacher, the professor, was an absolute idiot. And I dropped his class. And later, he sees me like walking in the hall and says, "Hey, how you doing?" And he says, "I remember you." You know? It's like, guys, I remember you're in my class. It's like, I didn't take it personally that you dropped. It's all cool. And I thought, well, you should have taken it personally. And then maybe you could up your game and teach a better class. Okay. All right.
Nobody dropped this one.
No.
What's drop?
Oh, yeah. Good. Yeah. No one dropped this one.
You need
So
to send that message to a few other people.
Yes.
maybe you should have taken it personally. All right. Quiz 8. All right, number 1. An NBC Wall Street Journal poll asked adults monthly in general, do you approve or disapprove of the job Barack Obama is doing as president? So we've got June 2009, we've got 2010, 2011. We've got approved, disapproved, not sure. All right, we're going to test the null hypothesis that approval rating is independent of survey date. And we're going to look for overwhelming evidence to the contrary at the 5% significance level using the chi-square test statistic. So, if approval rating is independent of survey date, what would you expect those numbers to be? Some of them would be all the same. Which ones would be all the same? All right, well, let's turn the page. And let's look at expected. For about an hour ago. Or 2 hours ago. All right, so look at the expected values and tell me which ones are the same and why you would expect those ones to be the same under the independence hypothesis. Yeah, so the proves would all be the same. Disapproves would all be the same. Not sures would all be the same. Why would those be all the same under the approval rating is independent of the survey date hypothesis? Yeah, that's true mathematically, but just tell me the intuition there. All right, it's late. Go ahead, Carlos.
What? Because everything would have stayed the same because it was expected to stay the same.
Yeah,
From the original observation.
Yeah, if date is independent of approval, we would expect the approval to be the same at all 3 different dates. Right? It doesn't matter whether it's 2009, 2010, 2010. You're still going to have the same amount of approval, disapproval, not sure for Barack Obama. That's the null hypothesis. The alternative hypothesis is that date matters. The date is not independent of approval rating, meaning the date means more or less likely to approve or disapprove. So, expected, approved, disapproved would all be the same on every date. So let's find the difference for each cell. And the difference is observed minus expected squared divided by expected. We do that 6 times. And we calculate our chi-squared stat of 113.10. And we need to know our critical value at the 5% significance level. To do that, we need degrees of freedom, which is rows minus 1 times columns minus 1. So 3 times 1 times, 3 minus 1 times 3 minus 1. 2 times 2 is 4. We look in the back of the book, chi-squared, 5% significance level, 4 degrees of freedom. We get 9.488. And you reject. Yeah, it definitely matters what date you asked. It would definitely affect the... So I would definitely queue this up in Excel. Some of the students Monday night were very frustrated by the Excel exercises. I don't know if you all had the same experiences. I would. You were frustrated by it?
Because you have to become an IT person, because the Excel that you have, if you don't know macros, you have to install an add-on. So just using Excel.
Yeah, that was part of the reason why I said for this week's Excel, do what helps you. Don't worry about it if it doesn't. We'll do what you did on the quiz. It seems like most people were pretty successful on the quiz. But one way I think is pretty straightforward is just do 3 different tables on Excel. Do your observed, your expected, and then manually type in observed minus expected squared divided by expected. You can even manually type that in 6 times, or if you know how to do with the $sign thing, you can do it that way. Okay. We could do the last one if you want, but it's the same thing. Alright. I'll be around if anyone wants to go over the last one, or any other questions you have. Yeah, the final will be on Blackboard, just like all your other quizzes. Yeah, you have to take it during class time. 2.5 hours. 3 hours. 2.5 hours. Oh, excuse me. Alright, so a two-tailed test because the slope is 8.5. This slope. So, no, this is the sample slope. We estimated this for like time online. We would say for every hour you spend online, your estimated is probably like 22, and for every hour you spend online, let's say you spend $40. Now this would be unique also. Like this were -4. So you spend 1 hour online, I would say you would spend $4 Well, we don't always do tell because slope could be positive or negative. Yeah. So, and we want to know if it's different from 0. It could be negative different from 0. It could be positive.
So there was the one.
Yeah, what happened, Loso? Can you say Loso?
There's not a one-tailed test for slope. Yeah, because slope could be positive or negative, so we just want to know. We didn't know whether it would be positive or negative. We started this.
I didn't even look because you haven't put
That was exactly my point.
I just say, listen, I apologize, but I hope you're not going to adopt me.
Oh.
You could see,